Welcome to the paper of numerical methods in the subject of information technology. Our today's point of discussion is open type Newton-Cotes integration formulas and Gauss Quadrature formulas. In our previous module, we studied closed type Newton-Cotes integration formulas. These were arrived by approximating function by a polynomial over the interval a to b, where a is x0 and other abscissas are x1, x2, xn lying within the interval where xn equal to b. These were closed type because our x0 was a and b was xn, and then to get the integral formula we approximated the function by polynomial passing through these abscissa points and then integrated this polynomial to get the approximate value of the integral. Today we will focus on the open type Newton-Cotes formulas in the beginning. See, in the case of open type, the endpoints are not included as abscissas. So, if you look at the diagram, the points are a, let us for convenience call it x minus 1, and the known abscissas which are being used to calculate the weights in the integration formula are x0, x1, x2, xn, all lie within the interval. So, x0 less than equal to x1, less than equal to x2, so on, less than equal to xn, and then finally the endpoint b. All these points are equidistant. So, xi minus 1 is equal to h for all I 1 to n, as well as x1 minus x0 minus a is also h and b minus xn is also h. For convenience, we can denote a as x minus 1 and b as xn plus 1. And so, we can say the interval is x minus 1 to xn plus 1, and so our h, now there are n plus 1 subparts of this interval. So, h is the h, that is the distance between any two consecutive points, any two consecutive abscissas. H is given by b minus a upon n plus 2. Now, the method of derivation is exactly similar. We approximate function by polynomial passing through x0, y0, x1, y1, xn, yn and integrate this polynomial. The only difference is the limit of integration. There the limits of integration were x0 to xn in calculation of weights. So, there the weights in the closed type was x0 to xn lix dx. Now, the weights are wi's as it is x minus 1 to xn plus 1 lix dx. So, the process is very similar, the method is very similar. So, we do not repeat the same exercise again, it is very similar, only limits are different, and directly I mention you the formulas which we arrive at using this technique. In the case where, first let us begin the case, the simplest case, and that is n equal to 0. So, only one point x0, interval is a to b, x0 is the midpoint, a is x minus 1, b is our x1, h I can say is b minus a upon 2. And here x minus 1 to x1 fx dx is 2h into fx0 plus 1 by 3 h cube second derivative at the point c. For convenience, we are using the compact form. The last term which you are seeing is the error term, and the integral formula is simply 2h fx0, which is also called midpoint rule. x0 is the midpoint of the interval, length of the interval is 2h. So, we are simply approximating the integral x minus 1 to x1 fx dx by 2h into fx0. Let us look at the 2-point formula now. So, the 2-point formula will be, the points are a is x minus 1 and 2 abscissas, so x0 and x1, and finally the endpoint b is x2. And so, x minus 1 to x2 fx dx is approximated by, the formula comes out to be 3h by 2 into simply the sum of function values at the point x0 and x1, that is 3h by 2 into fx0 plus fx1 in the bracket. This is the approximating integral open type Newton-Cotes formula for n equal to 1, and error term comes out to be 3h cube by 4 second derivative at the point c. Similarly, the 3-point Newton-Cotes open formula is x minus 1 to x3 fx dx equal to 4h by 3 inside the bracket 2 fx0 minus fx1, 2 fx0 minus 2 into fx1 plus fx2 plus the error term is 14 by 45 into h raised to 5 into 4 derivative at the point C. Now lastly, let us take the case of 4 point Newton-Cotes formulas. H is b minus a by 5, the point says a are x minus 1 and then x0, x1, x2, x3 and b is x4. And so the integral formula x minus 1 to x4 fx dx is 5h by 24, 11 fx0 plus fx1 plus fx2 plus 11 times fx3. And error term is 95 by 144 h raised to 5, 4 derivative at the point C. So the method as we have pointed out is exactly parallel to the closed type integration formulas number 1. And second thing, if you look at these formulas, of course they are very simple, coefficients are very simple integers, but if you look at the error term, there is no advantage in these error terms, they are of the same order. So as such they do not offer to us any benefit over the Newton closed type integration formulas. The only point where they are useful or they need to be applied are if the function has a singular point at x equal to a or at x equal to b. So at end points, if the function is singular, means the function is not defined or it is becoming infinity, like for example sin x by x. If we wish to integrate 0 to 1 sin x by x, at the point 0 the function becomes 0 by 0. Or let us say 1 by x and the one of the point is 0, end point is 0. So again that raises a problem. So in those cases, so if the function is unbounded at one of the end points or is an improper integral and a to b fx dx cannot be used, function value at a or b cannot be used, at that time these open type integration formulas are very helpful. They are also helpful in finding numerical solution of differential equations. So with this we would like to move to another type of numerical integration formulas, which are Gauss Quadrature formulas. So now let us look at the Gauss Quadrature formulas. See, Gauss Quadrature formulas are of the form a to b fx dx as w1 fx1 plus w2 fx2 plus so on wn fxn, that is sigma I equal to 1 to n wi fxi, where our weights as well as abscissas are unknown. So we derive the abscissas also and weights also in such a manner that this formula is of highest precision possible. So this is of the type where abscissas are unknown as well as weights are unknown. So if we try to derive the general form, there are 2n unknowns x1, x2, xn and weights w1, w2, wn. In order to find the formula, we will assume that this formula gives us exact answer when fx is a polynomial of degree less than equal to 2n minus 1. So formulas will be of the precision 2n, giving correct results for polynomial of degree 0, 1, polynomial of degree 1, x, degree 0, 1, 2, 3, so on up to 2n minus 1. Now let us derive these formulas one by one. We will begin with the simplest case. And in the beginning we will focus on the method which is known as method of undetermined coefficients. This is a very self-starting method, works from scratch. There are general theoretical developments also in this topic. We will look at those general theoretical development in the later section of this module. Let us take the simplest case when n is equal to 1. Now for simplicity, instead of taking fx to be a general polynomial of degree 1, 2, 3, so on, we will assume that this results for our convenience of calculation. These formula give us correct result when the function is 1, x, x square, x cube, so on up to x raised to 2n minus 1. Now let us take the case n equal to 1. In n equal to 1, the formula becomes of the form a to b fx dx is equal to w1 into fx1, where there are two unknowns now, x1 and the weight w1. So we will assume this gives correct result when fx is 1 and when fx is equal to x. So let us substitute in this equation a to b fx dx as w1 fx1 and equate both the sides. When fx is 1, we get a to b 1 dx is equal to w1 into function is 1. So a to b 1 dx is equal to w1. Integrate 1, the integral is x, limits are a to b, so we get the answer b minus a. So, we get the first equation as w1 is simply b minus a. And secondly, we put fx equal to x here. So, a to b x dx is equal to w1 into x1. Integral of x is x square by 2, limits of integration are a and b. So, we get the answer b square minus a square by 2 is equal to w1 x1. Already we have got the value of w1 as b minus a, we substitute w1 as b minus a here, which gives x1 is half into b plus a. And that is how we substitute the value of x1 as half b plus a and the weight as b minus a. Our formula becomes a to b fx dx as b minus a into f at the midpoint a plus b by 2. Actually, this formula is same as which we discussed as a midpoint rule in the case of open Newton-Cotes formulas. You can look at the graph shown here. It is like a rectangular rule, value of f at the midpoint a plus b by 2 multiplied by the width of the interval over which we are integrating, that is b minus a into f of a plus b by 2. Let us go to derive higher order formulas, that is when n is 2, 3 and so on. Now, see, when we will apply this method, the equations which will arrive will substitute fx equal to 1 and so on, will get 2 in equations to be solved in 2 n unknowns, namely the unknowns being x1, x2, xn and w1, w2, wn. Now, these equations which we shall obtain are non-linear in nature. So, for our ease of convenience of calculation of solving these non-linear equations, rather than working with the general interval of integration a to b, what we do is we transform this interval of integration from a to b to simple symmetric interval, very simple, minus 1 to 1. We can transform the interval a b to the interval minus 1 to 1 by simple change of variable given by x is equal to b minus a by 2t plus b plus a by 2. So, our dx is b minus a by 2 dt. When our x is equal to a, we get the equation a is b minus a by 2 t plus b plus a by 2. On solving, it simplifies to t equal to minus 1. And similarly, when x is equal to b, we get b is b minus a by 2 t plus b plus a by 2. Take b plus a by 2 on the left side, we get b minus a by 2 t is equal to b minus a by 2 t, and so we get the value of t as 1. So, our limits of integral change from a and b to minus 1 and 1. X is given by b minus a by 2 t plus b plus a by 2. So, a to b fx dx is equal to our dx is b minus a by 2 t dt. So, b minus a by 2 outside the integral sign and minus 1 to 1 f of b minus a by 2 t plus b plus a by 2. So, we will now our problem of integral of a to b fx dx gets transformed to the integral minus 1 to 1 gt dt, but let us say minus 1 to 1 fx dx. So, now we shall derive the formula for evaluating minus 1 to 1 fx dx. Our case is now n equal to 2. So, we want the formula of the type minus 1 to 1 fx dx equal to w1 fx1 plus w2 f at the point x2. x1, x2 are abscissas which are unknown and w1, w2 are weights which are also unknown. There are 4 unknowns, we need 4 conditions to solve them. So, we assume that this formula gives correct result when fx is a polynomial of degree less than equal to 3, 2 into 2 minus 1, that is 3. So, this should give correct result when fx is 1, when fx is x, when fx is x square and when fx is equal to x cube. So, in this equation we substitute one by one these values of function and derive the equations which need to be solved to enable us to get the values of x1, x2 and w1 and w2. So, we substitute fx equal to 1 first. If you put fx equal to 1, we get the right side is w1, f is 1. So, w1 plus w2 equal to integral minus 1 to 1 dx. Integral of 1 is x, limits are minus 1 to 1. So, 1 minus minus 1, the value of the integral is 2. So, our first equation formed is W1 plus W2 is equal to 2. Secondly, we put fx equal to x. See, fx equal to x is odd function, integral of this over symmetric interval minus 1 to 1 will come out to be 0. So, when we put fx equal to x, integral is x square by 2, limits minus 1 to 1, function is same at minus 1 as well as at 1. So, 1 by 2 minus 1 by 2, the value of the integral is 0, and the right side is W1 into f at x1 is x1, f at the point x2 is x2. So, we get W1 x1 plus W2 x2 is 0. This is the second equation. Thirdly, we put fx equal to x square. This is when we put fx equal to x square, the right side becomes W1 x1 square plus W2 x2 square. Integral of x square is x cube by 3. So, we get the value minus 1 to 1 x cube by 3, the values becomes 1 by 3 minus 1 by 3. So, we get the value 2 by 3, and finally, we put fx equal to x cube. Again, this is odd function, integral will be 0. So, we get W1 x1 cube plus W2 x2 cube is equal to, we can also see it as integral of x cube is s raised to 4 by 4 minus 1 to 1, function is same 1 by 4 minus 1 by 4, the value is 0. So, finally, we have 4 equations to be solved in 4 unknowns W1, x1, W2 and x2. These equations are W1 plus W2 is equal to 2, W1 x1 plus W2 x2 is 0, W1 x1 square plus W2 x2 square is 2 by 3, and W1 x1 cube plus W2 x2 cube is 0. Let us solve these simple 4 equations. The second one gives us W2 x2 is minus W1 x1, and substituting this in the last equation, we get W1 x1 into x1 square minus x2 square is 0, substituting W2 x2 as minus W1 x1. W1 x1 is common. It can be concluded that W1 and x1 both will not be 0, their possibilities are ruled out. Neither W1 can be 0, neither x1 can be 0, and nor x1 can be same as x2. So, all this can be ruled out, details can be seen in the text, and so finally, we get x1 square equal to x2 square, both being different, we get x2 is equal to minus x1. So, we get x2 is equal to minus x1, substituting in the second x2 is equal to minus x1, we get the answer W1 x1 minus W2 x1 is 0, giving us W1 is same as W2. So, these two weights are same, W1 equal to W2, substitute in the first equation that the sum is 2 and both are equal, gives us that each of these weight is equal to 1. So, W1 and W2 are 1, x2 is minus x1. Now, substitute in the second equation. Let us substitute in the third equation, W1, W2 is 1. So, x1 square plus x2 square is 2 by 3, x2 square is same as x1 square. So, 2x1 square is 2 by 3, giving us x1 square is 1 by 3. So, x1 is minus 1 by root 3 or square root of 1 by 3 or minus 1 by root 3, and x2 becomes 1 by root 3. So, we have derived the formula minus 1 to 1 fx dx can be approximated by the formula W1 W2 being 1, simply the sum of function values at 2 points at minus 1 by root 3 and 1 by root 3. It is simply f of minus 1 by root 3 plus f of 1 by root 3. This is known as Gauss quadrature formula with 2 points. To derive the error term, we have to do the same procedure. The weights are given by the integral of, we have to approximate a to, the weight functions are given by the integral Lix dx minus 1 to 1. To derive the error term, the same technique as we have done in the previous module of Newton-Cotes integration formula is to be used. The only thing is now abscisses are known minus 1 by root 3 and 1 by root 3. Find the interpolating polynomials through them. So, that is find Lix expression to them and integrate minus 1 to 1. And this gives the error term. We are omitting for the sake of brevity the derivation of it. It gives 1 by 135 into 4 derivative at the point psi. It is expected to have the 4th derivative because we assume that this gives correct result for polynomials of degree less than or equal to 3. In a similar fashion, let us derive the integration formula when n is equal to 3. When n is equal to 3, there are 6 unknowns W1, W2 and W3, and we can derive the equations to be solved in the same fashion by substituting f(x) equal to 1, x, x square, x cube, x raised to 4 and x raised to 5 in this case, because n is 3. So, this formula gives us correct result when f(x) is a polynomial of degree less than equal to 2 into 3 minus 1, that is 5. So, we will get 6 equations to be solved in W1, W2, W3 and x1, x2, x3. These equations are: sum of the weights is 2, W1 plus W2 plus W3 is 2, W1 x1 plus W2 x2 plus W3 x3 is 0, W1 x1 square plus W2 x2 square plus W3 x3 square is 2 by 3. I mean, this can be done, derive them very easily the way we did in the previous example. W1 x1 cube plus W2 x2 cube plus W3 x3 cube will come out to be 0. Integral of x cube odd function. W1 x raised to 4 plus W2 x raised to 4 plus W3 x raised to 4, integral x raised to 4. So, it will be x raised to 5 by 5 and 2 times, so 2 by 5, and finally again x raised to 5 is odd. So, W1 x1 raised to 5 plus W2 x raised to 5 plus W3 x3 raised to 5 will come out to be 0. Now, we solve these equations, and on solving these equations x1, x2, x3 come out to be the roots of the cubic equation 5x cube minus 3x equal to 0. So, these three abscissas x1, x2, x3 in the formula minus 1 to 1 fx dx as equal to w1 fx1 plus w2 fx2 plus w3 fx3 come out to be minus root 3 by 5, 0 and root 3 by 5. And once we know these x1, x2, x3, substituting back in these 6 equations derived, we get the weights as w1 equal to 5 by 9, w2 equal to 8 by 9 and w3 equal to 5 by 9. And so, our integration formula becomes minus 1 to 1 fx dx as 5 by 9, f at minus root 3 by 5 plus 8 by 9 f at 0 plus 5 by 9 f at root 3 by 5. Let us take some illustrations. Let us take first a simple example. Let us say we are interested in evaluating 1 to 2 1 by x dx. This is nothing but ln 2. Integral of 1 by x we know is log x to the base e, and the values are 1 and 2. So, ln 2 minus ln 1, ln 1 is 0. So, value of the integral is ln 2. Let us apply our 2-point Gauss Quadrature formula, that is minus 1 to 1 fx dx is simply the sum of function values at minus 1 by root 3 and 1 by root 3. So, but before applying, because our limits we are trying to find is 1 to 2, we need to transform our given integral to the limits minus 1 to 1. So, our formula is x is b minus a by 2t plus b plus a by 2. A is 1 here, b is 2 here. So, the transformation will be fx is 1 by x. So, it would be limits become minus 1 to 1 and we get x is 2 minus 1 by 2t plus 2 plus 1 by 2t. So, it is 1 by 2 plus 1 by 2t. So, t by 2 plus 3 by 2. So, f of t by 2 plus 3 by 2, that is f of t plus 3 by 2 dt minus 1 to 1, and 1 b minus a by 2 is outside the integral sign. So, b minus a is 1, we get 1 by 2. So, our integral 1 to 2 1 by x dx which we are trying to evaluate comes out to be 1 by 2 minus 1 to 1 f of t plus 3 by 2 dt, that is 1 by 2 2 upon t plus 3 dt. Let us apply our Gauss Quadrature formula. So, it is 1 by 2, the value of 2 by t plus 3 at minus 1 by root 3 is 2 upon 3 minus 1 by root 3, and at 1 by root 3 is 2 upon 3 plus 1 by root 3. Usually it would be evaluated if we are using computer program. Here we can simplify manually. It gives, that is 2 outside, 2 by 2 is 1, and simply 1 upon 3 minus 1 by root 3 plus 1 upon 3 plus 1 by root 3. We can take LCM, it is 9 minus 1 by 3 and numerator becomes 3 plus 1 by root 3 plus 3 minus 1 by root 3, that is 6 by 9 minus 1 by 3. The answer is 18 by 26, that is 9 by 13. So, the value is 0.69230766923. If we compare this with the actual ln2 value, then the error is less than equal to 8.394 into 10 raised to minus 4. Splendid. Just taking the value of function at 2 points and summing it, we have got an answer which is correct to so many decimal places. So, it gives a very high precision and with very less computation involved, simply finding function at 2 points. And even if one desires a higher accuracy, the similar technique of dividing interval AB into subintervals and on each subinterval transforming the subinterval to -1 to 1 and applying the Gauss Quadrature formula, the technique of composite form can be applied to get desired higher accuracy. Let us take another example of evaluating 0 to 1 e raised to minus x square dx. We know that this forms a part of error formula. Now, this time let us evaluate it by using 3-point formula which we have derived. So, a is 0, b is 1, fx is e raised to minus x square. Again transform using the equation x is b minus a by 2 t plus b plus a by 2. So, it becomes the integral 0 to 1 e raised to minus x square dx becomes b minus a is 1. So, 1 by 2 in limits become minus 1 to 1 f of it becomes t plus 1 by 2 dt. And using 3-point formula we get f 5 by 9 function at minus root 3 by 5 plus 8 by 9 function at 0 plus 5 by 9 f at root 3 by 5. The answer is 1 by 2 5 by 9 into f at 1 minus root 3 by 5 by 2, 8 by 9 into f at half plus 5 by 9 f at 1 plus root 3 by 5 by 2. And calculating the substituting fx is e raised to minus x square, calculating the answer comes out to be 0.7468144584, where the true value is 0.7468241330, and so the answer obtained is correct 5 decimal places. So, here see the performance of the Gauss Quadrature formula has been splendid, just finding at 3 points and summing by small rational coefficients, it gives us very high accuracy. Now, this technique of undetermined coefficients which we have applied here in deriving basic Gauss Quadrature formulas can be applied in fact to any derivation of any type of integration formulas. It works from basics, whatever are the unknowns, your number of unknowns, assume it to be correct for the polynomials of the appropriate degree, substitute same way f x equal to 1x up to the degree desired, form the equations and solve these equations to get the whatever are the unknowns. Abscissa weights may be or both may be unknown, only weights may be unknown. So, you will get the Newton-Cotes formulas, or there can be even a mixed combination that some weights are unknown, some abscissa are unknown. So, all those formulas can be very easily derived using this method of undetermined coefficients. For just illustration, for example, let us just try to derive 2-point formula which should come out to be the trapezoidal rule. The a is x0, b is x1 and a to b fx dx as w0 fx0 plus w1 fx1, x0 and x1 we assume to be known. So, we are now using a different method other than what we use in the derivation of trapezoidal rule, namely the method of undetermined coefficients. So, x0 x1 are knowns, x0 is a and x1 is v and w0 and w1 are unknowns, and we will assume now this gives correct result when fx is a polynomial of degree less than equal to 1, meaning by when fx is 1 and when fx is equal to x. This will give us two conditions, two equations to be solved in unknowns w1 and w0 and w1. When we put fx equal to 1, we get the answer a to b fx dx as w0 plus w1, fx is 1. So, you get the answer b minus a is equal to w0 plus w1. Secondly, we put fx equal to x, integral is x square by 2, b square minus a square by 2 is equal to a into w0, fx is x. So, at x0 the function is a, at x1 the function is b. So, we get w0a plus w1b is half b square minus a square. Our h is b minus a. So, w0 plus w1 is equal to h, a w0 plus b w1 is h into b plus a by 2, and solving it we get the answer just substituting w1 as w0 minus h, and using this substitution in the second equation solving we get w0 is h by 2 and w1 is h by 2, and trapezoidal rule is a to b fx dx is h by 2 into fa plus fp. So, this is just illustrates you that this technique of method of undetermined coefficients, which is very straightforward, works from the scratch, can be used to derive any type of formulas. The question is that Gauss Quadrature formulas are to be derived by using only this technique, or there is some solid other theoretical foundation with which these formulas can be represented. The answer is yes, and for Gauss Quadrature formulas, there is a very strong underlying theory of orthogonal polynomials, and using those theoretical developments of the orthogonal polynomials, the Gauss Quadrature formulas have been developed long in the long past era. We may not be going under the theoretical development, but the results are worth mentioning. So, let us just mention the results. The formula A to B Px into Fx dx, this Px is called weight function. So far we were integrating A to B Fx dx, so Px was 1 in our consideration. So, general treatment is A to B Px into Fx dx is equal to sigma I equal to 1 to n Wi Fxi. This is the type of formula, Gauss Quadrature formula, which we are deriving. Px is weight function, and this formula should give us correct result for Fx to be a polynomial of degree less than equal to 2n minus 1. So, this formula will give correct result. In this, the xi's unknown, which are supposed to be unknown, turn out to be the roots of phi nx. Now, what are these phi nx? Phi nx is a polynomial of degree n. Now, what kind of polynomial it is? See, phi nx, first thing is a simple set of polynomials, and it is orthogonal. Not only it is a simple set of polynomials, phi nx are orthogonal with respect to weight function Px over the interval AB. What does this mean? First thing is, a simple set of polynomials means you have a class of polynomials where phi 0 is constant, phi 1 is linear, phi 2 is polynomial of degree 2, phi 3 is polynomial of degree 3, and so on. So, for example, 1 x, x square, x cube is also a simple set of polynomials. But not only this, this should be orthogonal set. Now, when is phi nx said to be orthogonal set of polynomials? If it satisfies A to B Px into phi nx, phi mx dx is 0 when n is different from m and is non-zero when n and m are same. It is like your vector product, the dot product is 0 for different vectors if they are perpendicular. Same concept has been extended to polynomials, and the inner product is nothing but the integral A to B Px Fx into Gx. Inner product of two functions Fx and Gx is A to B Px into Fx into Gx dx. So, phi nx said to be orthogonal set of polynomials if they are simple set of polynomials, and A to B Px phi nx phi mx dx is 0 for n different from m and is equal to Gn non-zero for n equal to m. So, if phi nx is a set of orthogonal polynomials with respect to weight function Px over the interval AB, then in the formula A to P Px the Fx dx as given by sigma Wi Fxi I equal to 1 to n, the unknown abscissas come out to be nothing but the roots and roots of phi nx. And once we know these x1, x2, xn, then the weights are determined in the same fashion. Wi's are nothing but A to B Lix dx, where Lix is the Lagrange coefficient given by product of x minus xj upon xi minus xj, where I is different from j. So, those who are interested in learning about this result, how it is arrived at, and the theoretical development are urged to refer Froberg, Hildebrand, Brady, Chennai. All these books contain good theoretical development about the Gauss Quadrature formulas. So, it begins from the discussion of orthogonal polynomials and goes up to Gauss Quadrature formulas. Now, let us just cite a few Gauss Quadrature formulas. Of our Px is 1, if the interval of integration is minus 1 to 1, we get minus 1 to 1 Fx dx as W1 Fx1 plus W2 Fx2 plus Wn Fxn. Their x1, x2, xn are zeros of Legendre polynomials P and x. where P0x is 1, P1x is x, P2x is 3x square minus 1 by 2, P3x is 5x cube minus 3x by 2, and higher order Legendre polynomials can be derived by using the recurrence relation Pn plus 1x is 2n plus 1 by n plus 1x Pnx minus n by n plus 1 Pn minus 1x. The formulas which we derived using method of undetermined coefficients were nothing but the Gauss-Legendre formulas with n equal to 2 and n equal to 3. Similarly, if the Px is e raised to minus x and interval of integration is 0 to infinity, open from the infinity side, in that case 0 to infinity e raised to minus x fx dx can be given as sigma wi fxi. Here the xi's are the zeros of the Laguerre polynomials. Now, Laguerre polynomials are orthogonal with respect to e raised to minus x on the interval 0 to infinity. Laguerre polynomials are denoted by ln x, where L0x is 1, L1x is 1 minus x, L2x is x square minus 4x plus 2, L3x is minus x cube plus 9x square minus 18x plus 6, and recurrence relation is given by ln plus 1x is 1 plus 2n minus x ln x minus n square ln minus 1x. And similarly, if Px is e raised to minus x square on minus infinity to infinity, then x1, x2, xn are zeros of Hermite polynomials h and x given by h0x is 1, h1x is 2x, h2x is 4x square minus 2, h3x is 8x cube minus 12x. And recurrence relation for Hermite polynomial is hn plus 1x is 2x hnx minus 2n hn minus 1x. And finally, if Px is 1 upon root 1 minus x square on minus 1 to 1, then x1, x2, xn are zeros of very famous, very much used Chebyshev polynomials t and x given by t0x is 1, t1x is x, t2x is 2x square minus 1, t3x is 4x cube minus 3x, and recurrence relation for this Chebyshev polynomials is tn plus 1x is 2x tnx minus tn minus 1x. Using these recurrence relations, higher order polynomials can be easily constructed, so and roots of these polynomials can be found out. So, x1, x2, xn can be very well derived, and then using the weight formulas, the weights can be derived. Of course, so what we have learned is about this Gauss Quadrature formulas, they are give us very excellent results with very low computations. In pre-computer eras, these Gauss Quadrature formulas were not very favorite with the users for the simple reason they involve the abscissas as irrational points, so which required the evaluation of function at irrational points. But now with the advent of computers, it hardly matters at what point the function is being evaluated. So, here weights are also very simple, all it requires is, so their computations are very low and very good desired accuracy can be obtained by Gauss Quadrature formula. These all Gauss Quadrature formulas have come out to be open type formulas, abscissas lie always within the interval, and so they can also be used for again improper integrals and for other cases. So, thank you very much. So, this completes our chapter on numerical integration, and for further reading, of course, there is lot, because numerical integration is a very stable process being area under the curve. The errors in the areas are very, very low compared to the entire area under the curve, and so lot of development is there, lot of other more superior techniques and modifications are there. So, those who are interested in learning further can refer to the books mentioned in the references. So, once again, happy reading, happy learning. See you again for the next chapter.